Uh, Hello, everyone. I guess we'll start. It's 5:50. So this is my name is Sergey Sheluhin. I'm a software developer with Hornworks, and I'm going to talk today about LLAP, which is so to speak, a Hive's answer to data warehouse and BI analytics, SQL BI analytics. So this talk is going to go like this. First, I'm going to cover what LLAP is. Then I'm going to cover how LLAP sort of integrates into the BI solution for the cloud and on-prem clusters. And I'm going to talk a little bit about different areas of the design, query execution, security. I'm going to talk about how it works for other non-Hive scenarios. And if we have time, I'm going to cover a little bit about how to run it. Otherwise, we're just going to give a bunch of links, and that will be it. So we'll start with just, I call them old slides because I use them every talk. I'm going to start with a brief overview of what LLAP is and basically what it represents. I'm assuming everyone is more or less familiar with what Hive is. So Hive is a query execution engine on Hadoop in the most simple case. And it has roots in MapReduce, so it used to run containers in order to do work. So what LLAP basically is, it's a hybrid model of execution where you have you may have some containers, but also you run some of your work inside the persistent daemons that run on every node or a subset of nodes on a cluster. You are still using the same infrastructure of Hive, so using the operators, the data pipeline, but in addition, you get all the advantages and I guess potentially some disadvantages of running in a persistent daemons. And you get such things that are possible to optimize with the persistent daemon. You get caching, you get some synergy between different queries running together. One important point is that just to sort of dispel a common misconception is that LLAP is not an execution engine. It does not replace Tez, or it's not like a Mara Spark. And it's not a storage engine, so it still reads the same data that Hive reads normally from HDFS, Azure, Echelon, what have you. So here I have a little slide with kind of like a high-level overview of how everything happens. LLAP is transparent for the users of BI tools or the users of Hive. You have a JDBC connection to Hive Server 2, and Hive Server 2 basically handles the query orchestration for you. Except instead of running containers, the query may run entirely or partially in LLAP daemons. So again, just to reiterate, LLAP pretty much is Hive, so it supports all the format that Hive supports, like, for example, Parquet or Orc, although not all formats may have all optimizations enabled that I'm going to talk about, but I'm going to cover this throughout this talk. Hive Server 2 coordinates the sessions, the concurrent sessions, and Tez AM, just like with the regular query, coordinates work between different daemons. And in the past, we were saying that we basically fully support hybrid execution model between containers and LLAP, where some queries run containers and some LLAP. We still do support that. But after our own internal performance testing, we actually recommend running most of your workloads on LLAP. So by default, you should run everything in there, unless you have some restrictions related to security, for example, like temporary UDFs and user code that is not added by administrator. But so you should run everything in LLAP, and only if you actually run into scaling issues, which is highly unlikely, you should try to switch to containers. And the key advantages of LLAP for the BI system from the perspective of sort of running this thing on a high, like kind of 50,000 feet level view is that you get a single engine, you get a power of Hive scalability and fault tolerance for ETL queries and for large queries. As I'll mention later, we're actually running TPCDS 100 terabyte scale, and it's running pretty well. At the same time, you get all the features of Hive, like ACID transactions and the cost-based optimizer and NC-SQL support, while also getting the advantages for BI queries, such as fast processing and intelligent scattering of BI and ETL workloads running together. In addition, although this is kind of like a new functionality that I'm going to cover, you get a text cache which supports zero ETL analytics on the cloud. by basically converting the text to efficient format on the fly. And also in the works is the external access for non-Hive tools for Hive data and features, for example, the access from Spark. So now the new slides, or at least partially new slides, about the efficient BI query execution on LLAP. So I'll start covering the basics, namely the actual execution of the queries. And here's another kind of simple diagram. So if you think about the TES or MR or Spark containers running on a node, in the same way, you can see that there's one single thing running on a node, which is LLAP, which hosts a number of executors. And executors execute so-called work fragments, which are basically the equivalent of tasks, except they share the same process. And they use the same functionality of reading the file system and sort of exchanging the data like shuffle as the containers. Inside of the daemon, we have a queue for work with configurable priorities. So as soon as the fragment finishes, the next fragment starts. And the queue is somewhat intelligent. It tries to optimize to run BI queries first. And so if the query is shorter, it's going to finish faster. It's more latency sensitive. And it also has some support for parallel workload efficiencies, which I'll cover in the next section. So from the start, you get all the advantages of just running in a single JVM instead of running in multiple JVMs before we even start doing optimization. So for running a single query this is with cache disabled and with a similar environment, with running on, so this is just one of the TPCDS queries, running on fresh new containers, it runs for about 20 seconds. After you just start LLAP and run the same query, it speeds up by about a third. And after you run the query a few times, various things happen even without cache. Like, for example, JIT optimization kicks in the JVM. So like the warm JVM runs much faster than cold JVM, so the query speeds up even further. And to just provide a summary slide, this is LLAP compared with old Hive 1. And we find that on most TPCDS queries, it's just ridiculously faster. And the average is 26 times. Well, the total time is 26 times speed up, whereas individual queries can go as high as, I don't even know what this is. I think like 45 times faster. Obviously, it's not like some queries, it's going to be just only 5 times faster. But basically, it's much faster out of the box. This is with cache enabled, though. The main comparison we are doing, though, for the single queries is obviously with Impala. And we ran some benchmarks on the recent version with a 10 terabyte data set for TPCDS on 10 nodes. We were able to compare 57 queries from TPCDS data set. As of the recent version of Hive, Hive supports all 99 TPCDS queries. 2 queries require configuration changes that are not standard, but all the queries run after that. Impala, we were able to run 57 queries. Most of them have some SQL shortcomings, and 3 had issues with crashes and failures. So as you see, for the total of 57 queries, Hive is actually a little bit faster than Impala. I do have to admit that we are not actually faster than Impala overall yet. Most of this comes from the cases where when Impala is slow, it is really slow. So Hive, I think, is faster on about a quarter of the queries. But I think the key point is that it's actually in the ballpark, and the runtime for most of the BI small queries is very similar. And I actually have a slide which is probably kind of hard to read, which has a logarithmic scales on different queries on HTTP 2.6 and CDH 5.11. So this is a logarithmic scale runtime, and lower time is obviously better. So this is the single query efficiencies that come from the execution pipeline. And now we'll talk a little bit about the parallel query execution. So right now, the parallel query execution in LLAP is sort of in its infancy, but it's already showing a lot of promise for scalability for parallel workloads for multiple users. And this comes both from the efficiencies over containers in terms of just how you run the work in the single daemon instead of the containers, and the sharing of the cache, and some additional features like sharing of a hash table loading if you're doing a map join. But also we have some features, for example, preemption. Like, for example, Hive runs pipelining in the reducer stages. So when the reducer stage is not yet ready to run because some inputs are missing, it can still run and start downloading the inputs before they're all ready. So what might happen is that you're running all those reducers that are downloading some data but not ready to finish yet. And then you're running a BI query. And your BI query in normal circumstances is going to be queued behind your ETL query, and it's going to take forever from the user's perspective because it's not running any work. So it turns out if you are actually aware of what your work items are, unlike in a container case, and they're not as sort of heavyweight as they are in a container case, you can actually preempt work. You can say, hey, I have this reducer that is not super important. Let me preempt it and run my interactive query first. So your short-running query might just like kind of come in, take a little bit of capacity, finish, and then the ETL query will continue with minimal loss of performance. Whereas for the BI query, it will be a significant gain on latency. Another thing, first of all, I'll actually show the performance slide. This is a run limited to interactive queries, so this is running only short queries together. And as you can see, the scale, it's actually pretty much linear scalability of running concurrent, like 5, 25, 100 concurrent queries in parallel on LLAP. This is in its current state as of 2.6. So we also have some future work planned for improving concurrent query execution further. And this is the central workload management. So this is actually something similar to what you have in the classic sort of data warehouse solutions like Oracle, or, well, I mean, most data warehouse solutions, is where you can have a flexible system for policies, where you're saying, you know, I have many users like sales and marketing are using my database, and I want to give half the cluster to sales and half the cluster to marketing. And maybe I want to give a special allocation to marketing with some very important jobs that are going to run with high priority. So, and this is work in progress. This is not something that we have right now, but this is like coming in the next version of Hive and LLAP, is where you'll be able to specify the SLAs. You're going to be able to ensure the SLAs for queries by specifying the priorities and fractions of the cluster. So, and you'll be able to split your queries manually into BI and ETL workloads, or sort of make sure the cluster is shared fairly between your users. For example, that if users run multiple queries, they get equal resources, or they run in order. And in addition to that, given that we are running a custom scheduler, so we are more flexible than Yarn because, again, we know what the work is. We can also do some additional improvements. For example, we can see what are the fragments doing, what data are they reading. If some query, so the query starts and we think it's a BI query, but it runs for a really long time and reads a lot of data, we can say, okay, actually it's not a BI query. It's probably a slow query, so we can reduce the priority dynamically based on what administrator has specified for this case. And we can move, for example, we can even pause the query and make sure that it doesn't get any resource allocation at all for some time, except for scraps left over from other queries. So this is something that you can look forward to in a future version of LLAP and Hive. So the second pillar of the BI workloads in optimization, especially in the cloud, is caching. So let's talk a little bit about caching. We have a cache that's fully buzzword compliant. So it's columnar, it's pretty compact, and it's prioritized. These things are pretty important when you have filters and projections, because you don't want to cache the data that you never read. And you do want to, if the data doesn't fit in memory, you still want to try to optimize your reads from the cloud file system, especially by seeing the indexes first and saying, maybe I don't need some data, and so I'm not going to read it. So it's basically PPD without actually going to disk. The cache is off heap, so it doesn't produce extra garbage collection, pretty much. And we also have support. This is a kind of a new feature. We also have support for SSD caching. SSD caching is actually not as important on-prem, but it is a huge deal on the cloud where the reads are extremely slow, and also you actually pay money for the reads. So if you don't have to pay money for the reads, it's good. And even if the disk may be slower than, well, not slower, the disk is slower than memory, like as slow as a file system, it's still good to not pay money for the reads. We also have intelligent eviction policy, which uses LLAP, which is at least recently frequently used hybrid that makes it somewhat resistant to large scans that can wipe out your cache and tries to preserve the better cache hit ratio for small queries that read frequently read data. So as I mentioned, on-prem and on large queries, the cache may not make your queries much faster, especially if it's in memory cache, because your data simply won't fit in it. However, it becomes much more important as your queries become smaller, as you move to the cloud, and especially if you are going to run with the text data. If you're using text cache, because of the way the text cache works, which I'll cover in a few slides, your queries become much faster. So I'll just go into a brief overview of how this works. You basically have your read planner that plans the data between disk and cache, depending on what you can find in cache. And as we read the data, we decode it, and we preserve the data in a sort of like a decompressed but encoded format in the off-heap cache and an SSD cache. And the next time when a read planner comes for the same query or a different query, even from a different user that reads the same data, it will potentially read the data from cache and get better performance, better results, less reads. So this is actually a relatively new number. It's from last week. And unlike most performance benchmarks, including most of the ones in this talk, this is not super optimized. So don't take absolute numbers as like the best possible result. But it does indicate a pretty good speed up from a cache on a 100 terabyte TPCDS data set. So these are runtimes for queries sorted by speed up 100 terabyte ORC, a TPCDS data set with SSD cache. And SSD cache is, I think, 400 gigabytes per node, so it's pretty big. And on the best queries that you see on the left side, the speed up is up to 10x. And on the median query, it's about 2x, and 1.x, or average speed up rather. And on the small queries, it's about 2.1, 2x. So that could be a pretty big deal on a cloud file system. In addition to the columnar cache, which we support for ORC right now, and we are working on columnar cache for Parquet. Again, I just have to say LLAP can run queries on Parquet. It will just won't use the columnar cache. Right now, we are working on it. We also support zero ATL analytics on the data like CSV and JSON, which is basically text data. And the way the text cache works actually is like this. Say you run the first query, which looks kind of similar to how ORC works, except it entirely bypasses cache on the read phase because there's nothing in there for this particular data. We have a separate decoder that decodes cache into vectorized formats, decodes, so to speak. But however, something interesting happens after we have given the data to the user, to the operator pipeline to process. In the background, we actually have a lightweight ORC encoder that encodes the data into ORC. It's not full ORC. It's kind of like ORC-ish format, and puts it in the off-heap cache. So when your second query runs, I drew the arrows with dashes here because potentially it may combine some data from disk and some data from the cache. But what you really want to have, especially if you have SSD, is that you're basically reading ORC data, which is much faster because it's not text. And also, you don't go read these humongous text files from your Azure or AWS cluster that is pretty somewhat slower than on-prem file system. And we have some runs also for the text cache where the speedups are even more significant than with ORC's fastest query. And unfortunately, this picture is not a very good quality, but the fastest query is 38x speed up on a cloud file system with text cache. And this implies 100% text cache hit rate, which really depends on your data set size. But with SSD, you can comfortably ensure this 100% cache hit rate. So the usage patterns for BI, actually, something that I should mention for text cache also is that, for SSD cache, is that if you have configurable locality, you can have strict locality where the fragments will try to go to the place where the data is in the cache based on consistent hashing with some secret sauce on top for fault tolerance. And you can also, that is good when you expect a lot of benefit from cache like SSD. You can also relax locality, which has applicability in different scenarios where you have on-memory cache. And in that case, a typical BI access pattern is that you load the data periodically, and you have the data for the last day or last hour or last month or week, basically a unit of time, which is accessed frequently, and the rest of the data which is not accessed so frequently. So in that case, in a classic sort of caching or even storage solution, you can create hotspots where the recent data is being read and nothing else is being read. So in the case of LLAP, you have an option to relax cache locality, which basically means that shortly after running in the hotspot, the system will try to schedule the work in a different node and actually cache the data also in that node. So your cache will sort of automatically create multiple replicas of this data that will be used to avoid the hotspot over time. And in addition, for this usage pattern, if you are using ACID, which you should be using if you're loading data in Hive over time, it's out of the scope of this talk, so I won't go into details. But basically, because the cache is file-based and it's sort of automatically coherent, I'm not going to cover how ACID works, but basically when you're loading the data on top of the old files, the old file cache is not invalidated, and only the new sort of data needs to be read from disk. And this is sort of work in progress, because after the compaction, your data will still all be invalidated, but this is work in progress to make this work better with ACID. The point is that it's a pretty good fit for sort of ACID periodic load usage pattern for BI. So in addition to providing access this awesomeness for Hive, we wanted to share the joy and provide the access to LLAP from external components, like, for example, Spark. And this is in early stages of development right now, although we do have a blog post and it already works. So like, as I mentioned, Hive on Tez and other DAG executors potentially can use LLAP directly by submitting work to it. We also provide sort of a relational data node view of the data using an API. The API is not very well defined right now, so there's only like some code with Spark that that works, that you could potentially look at to use this. However, over time, hopefully the API will improve and become more standard and documented. So what it basically means is that you can push work into LLAP, and there are two main sort of scenarios for this. The first scenario is very simple, where you basically push a scan. And the advantage of just scanning the data from HDFS is, first of all, that it may be faster because you're reading from cache. In addition, it covers the cases where you need to make use of some Hive features that are not really supported in the other product. Like, for example, you can read Spark tables right now, Hive tables right now from Spark, but you cannot read ACID data because Spark org reader, last time I checked, I'm not sure, maybe it was fixed since then. Last time I checked, org reader in Spark cannot merge ACID delta files and basically read the ACID data correctly. However, if you're reading the data through LLAP, LLAP can read the data correctly and basically return the data to you the way it should be, and that will be true for basically all or most org features that you care to mention. And another scenario that can also be considered, even though it's not really used that much yet, is that you can actually put execution into LLAP, from a simple case where you can put a filter or a projection there instead of just putting like a scan, to the case where I think that actually already happens in Spark, to the case where you may even be able to put a join into LLAP. So as long as you can compile it and send it in, and you have the access to actually do that, you should be able to push arbitrary execution there. So that is something that is probably in the future for this model. So I'm going to cover like an example of usage of a very high-level Hive feature from Spark. So Hive with Ranger has this new feature that was introduced recently, which is column-level security, where you can specify a Ranger policy for column-level access restriction or masking for different users. So here I have some Ranger screenshots where we go to the customer table and specify that we're going to have a filter, which I guess is not shown here, and we are going to have a mask for the names of the customers for certain users. So here we go and run a query from the Spark shell, and we see that we have some customer names. So these guys have really cool customers. And the names are actually masked. We can only see first 4 characters on the name, and we can only see the male customers. However, as soon as we key in it with a different user, the billing department, which has wider access, you can actually run the same query from Spark SQL and you can get the full customer table, and you can actually get the full names of every customer. So this behind the scenes Spark SQL is running Spark, obviously, and Spark is using LLAP internally to get the Hive data, whereas LLAP inside applies these column level security filters on the data to return it to Spark, to return it to Spark SQL, to return it to Spark Shell, or it could be returned to some tool that you might use. And there's a link on the slide which has a blog post on Hortonworks blog about this feature. This basically describes it in more detail. So now let's talk about security, the topic that everybody hates talking about, but is actually pretty important for data warehouse. So I'll cover this briefly. We have a sort of recommended enterprise data warehouse usage pattern where if you're running Ambari, you probably run one single LLAP cluster that is centrally administered and shared by all users. And your security goes through Ranger or SQLOS, but Ranger is recommended. We don't recommend using DUES with LLAP. It's kind of outdated, and it's a pain. So basically, Hive super user through Hive Server 2 through Ranger manages your security and access to the cluster, and all the users get to share the cluster and share the advantages of caching, et cetera, et cetera. And the access to Hive Server 2 happens through JDBC, which can be used through Beeline, or it can be used through any JDBC supported tool like Tableau or what have you. So this is an architecture slide for security, which is there's lots going on this slide. But basically, people might recognize that this is typical Hadoop setup with file system tokens. By the way, the squares are tokens. If it's not, oh yeah. So these are tokens and keys. The only major addition is that LLAP and Hive Server 2 share a secret manager where they securely share a set of keys and tokens for the daemon. And each query gets its own LLAP token, which means when the query is running, it can only access its own fragments. It cannot access the fragments belonging to other jobs. Whereas inside the query, it's basically the same as regular Hadoop security, where the job-specific token is used for shuffle and some job internal things, and file system tokens, H-based tokens, et cetera, used for security inside the ecosystem. And Ranger gives you policies that actually tell you what you can access and how you can access it and what happens with all this. There's a little bit of a difference with external additions like Spark, because when we give sort of the Hive data tasks to the user, we cannot control what they do with them. They can modify them and send some malicious code. So what we do, we actually have a shared key also that we use for signing those. So we send a digital signature with a task. And when a client submits work to LLAP, LLAP can validate that the key parts of the code and stuff, like the file names, were not modified by the customer, so they cannot influence, cannot access the stuff they don't have access to. So we also have integration and tools. So I'm going to cover this really briefly, hopefully. There's integration in Ambari, and the key kind of to remember is that HTTP 2.6 is the GA for LLAP. You can use it in Ambari 2.5. It's called interactive query in Ambari 2.5, and you can enable it and configure it separately from the mainline Hive. This will go away in Ambari 3.0. It's going to be one unified Hive, which will include both interactive and the old Hive, so to speak. And even though it's called interactive query, as I again repeat, this is actually good for most workloads. If you should run the workloads there by default, if that doesn't work, which is highly unlikely, you should talk to us and then maybe run them in containers. I'll cover later how to run it without Ambari. Actually, probably I won't have time, so you'll have to look at SlideShare. So we also support LLAP in the cloud. It's supported on HD Insight using CloudBreak. Oh, sorry, HDC on AWS using CloudBreak and HD Insight. We have Tez UI integration with LLAP. On this screenshot, you can see that queries are running, and you can see LLAP application ID, so they're running in LLAP. And some other cool things in Tez UI are query swim lane, which shows you where the time went for execution, compilation, et cetera, and a DAG swim lane, where within this query execution time, you can see which mappers, reducers ran, what time did they take, what was the critical path of the query, like where is the time going. And in this DAG swim lane for LLAP, you can also see LLAP counter. So like, for example, in this case, you can see that the map, whatever the mapper was running, map 1, actually had 100% cache hit rate and metadata cache hit rate, so it didn't read any data from HDFS at all. We also have this, actually not related to LLAP, but we have this neat button. I just want to point it out on Tez UI. It's called Download Data, where you can get a lot of useful information for your query, explain plan, runtime, etc., to debug what's going on with the query. So LLAP also exposes UI for monitoring, which is basically accessible on every node. We don't have a central UI yet. That's work in progress. And it exposes some additional debugging tools like JMX view on every node, which has a lot of data. And we do have log download option in Yarn from the running LLAP cluster. You can download logs separately for every query. The log files are encoded with query file name, and the log lines are separated by queries. So running LLAP, I'll just give you a brief summary because we are a little bit short on time. So first of all, we do recommend using Java 8 and G1 GC because these are pretty big processors, and Java 8 is just way better, and Java 7 is like really old and I think maybe out of support by now. So yes, there are some kernel configs for TCP connections that are useful for large shuffles that will be on future slides and SlideShare. If you are using Ambari comes with reasonable Hive performance configs, but it may require some tuning for your specific workload. Without Ambari, you may need to tweak a bunch of configs for Hive performance that are going to be on the future slides and on SlideShare. We probably will publish a document for this at some point in the future so that you could tweak it for performance. Some new features like SSD and text cache require going to advanced config section in Ambari for now, and you have to specify the settings manually to enable them. They're not enabled by default. And the main thing is how you size your LLAP cluster is basically like this. So Ambari, again, if you have Ambari, it does a pretty good job out of the box. If you don't have Ambari, or if Ambari in your case for some reason doesn't do a good job, or you want to do a better job, you basically want to calculate the number of parallel queries and give each application master about 2 gigs of memory, and you want to spread them between the nodes. So you basically, if you have, say, 20 nodes and 10 AMs, you want to say that you want to take 2 gigs from each node. Or sorry, like if you have 10 nodes and 20 AMs, you want to take 4 gigs from each node, so 2 AMs per node. Then you give the rest of the memory to LLAP. Within LLAP, you can need to define a number of executors. Well, Ambari will define it for you, but again, you can tweak it. So you want to give about 3 to 4 gigs per executor, and then give rest to the cache. And without Ambari, look at Hive service LLAP command, and LLAP uses slider to coordinate, so you will have to use some slider commands to run the cluster. So I have a few more slides on this, which I'm going to quickly scroll through. They're all going to be in SlideShare. It's probably a good fit for SlideShare too, because they have a lot of numbers and config settings that are not amenable to pronunciation. So just to summarize, so you don't have to, there are 2 things that I wanted to take out of this talk. The first thing you don't have to remember, because I was practicing about reading this sentence. LLAP provides a unified, managed, and secure cloud-ready enterprise data warehouse solution for BI and ETL workloads via a fast execution substrate harnessing high vectorized SQL engine and efficient memory caching layer for columnar and text data. You don't have to remember all of that, but basically we have lots of buzzwords, and most of them actually work. And if you want to try, LLAP, you can do it today. LLAP is available as part of Apache Hive. It is available in Apache Hive starting with version 2.0. But for the best results, we recommend using the latest version. And actually, it's version 2.2 that is not released yet, but it will be soon. And if you want to ask questions about 2.2, the guy who is responsible for that is in the audience, so he will answer them. Hortonworks Data Platform 2.6 has the latest version of LLAP, and as I said before, the recommended version is the latest one, 2.6.1. You can also use LLAP on Hortonworks Data Cloud on AWS, and you have a link here. And you can use it in Microsoft Azure HD Insight that has support for both Spark and Hive LLAP on Azure. That's about it. Do you have any questions?
Can this collocate on the same nodes as the Yarn compute nodes, or is it not recommended?
So it is running on the same nodes. Sorry?
Can you repeat the
Can this collocate with the Yarn compute nodes? So LLAP is actually using Slider, which is a Yarn library for long-running services. So it is running on Yarn compute nodes using Yarn. We do not generally recommend splitting the cluster nodes in parts. So the general recommended pattern is if you want, say, half of your cluster to go to LLAP and half to containers, is to have half of your nodes run full-size LLAP and half of your nodes basically, well, if you run, say, on a 10 LLAP containers on 20-node cluster, you will naturally separate it in half. But if you want to, you can technically collocate them on the same nodes, yes. You just have to size the LLAP appropriately to leave some memory for the other tasks. Yeah.
Yeah, I have two questions. First question is the DAG different for Hive, query on Hive server 2 versus Hive plus LLAP?
So the question is DAG different from query on Hive server 2 versus Hive server 2 plus LLAP? Generally, almost in all cases, it would be identical. There may be some specific LLAP optimizations that are at this point probably pretty minor. Like, for example, different sizing for map joins that can change the DAG. But generally, it's an identical DAG.
Thanks. Second question is, within the Spark context, would we want, if you want to invoke Hive plus LLAP, do we need to do something extra, or it's the same libraries you're invoking from the Hive schema?
I'm sorry?
Running the Spark context at runtime.
I did not quite understand the question. So,
Within Spark 1.6 or 2, while running the Spark context,
yes?
do we need to do something extra to invoke Hive plus LLAP?
The question is, within Spark context, doing something extra to invoke Hive plus or Spark plus LLAP? You do need some extra jars. Unfortunately, I cannot answer this question off the top of my head. There was a link in the presentation to the blog post about running Spark on LLAP that might have more details on what you need to add to Spark context to run it. Sure.
So how does it compare with Druid?
So Druid is an OLAP query like the cube solution, right? Whereas this is sort of like ALTP or BI SQL query solution.
You're trying to make things like do analytics, fast analytics. So sometimes to do Hive LLAP is a few seconds. Sometimes to like do Druid. Probably time series data will be much faster.
Yeah, well, I guess it depends on the workload right now. I'm not extremely familiar. Unfortunately, I didn't go to the Druid talk, so I am not. Oh, perhaps the speaker can answer this question. So the question is, how does this compare to Druid, and like how do you use it at the same time with Druid, depending on the workload?
So Druid is more suitable for like time series. Yeah, because most of the
Yeah.
time part of the data, so more all tables. Right. So if you have non-time series data loop, like LLAP would like perfect.
I mean, so analytical queries, typical, like, TPCDS kind of queries. I'm not saying everybody just runs TPCDS, but, they're kind of representative of many queries that people run. They would probably be, Druid is not suitable for such queries, right? Whereas, presumably, some scenarios specific to OLAP type workloads that you could implement in SQL, but they're not really, it's not really the best instrument for the job, at least at this point. Yeah. Does this answer your question?
So for the numbers you obtain for Hive on tape versus LLAP with cache, how many times did you have to run the query to obtain those numbers?
That's a great question. So, which numbers are those?
Probably like fourth or fifth slide you have.
Oh, in the very beginning. Oh, this unfortunately I do not know. This might be, yeah. So unfortunately, this is one of the old slides. So by now, I do not remember this. I think it was using, so I think the case may be that the queries actually ran once, but they ran in sequence, which means that the queries were basically using the cache from the previous queries when they were running. Yeah.
Yeah, so regarding the caching part of it, right? So as LLAP is caching the data, and when how do you mark the state that when data is changing on the disk?
So we are using the famous feature of HDFS and pretty much all cloud file systems is that you never update the files other than appending to them. So the data is cached by basically unique. We know the uniqueness of the file, especially on HDFS, but also on Azure and S3. And so we don't need to do the actual eviction of the data based on the file being gone, because if somebody writes a new file with the same name, it will have a different ID and different metadata. So the old data will just eventually get evicted from the cache. It's possible to optimize it, I guess, to evict the data proactively, but in our experience, it was because usually this cache is like pretty well used on typical workloads, so it goes away pretty quickly.
And the data in cache is always encrypted?
The data in cache is not encrypted, it's encoded. So it's encoded for optimization for like columnar encoding, you know, like dictionary encoding and stuff like that. It's not encrypted. It's actually an excellent question. I probably should make a point about this. No, it does not support encryption right now. Oh, sorry. I'm kind of blinded by the lights.
So, what kind of the query complexity, right? If I have multiple joins, like 2, 3, and 3 times trying to join.
So
do I need to store it in by bucketing, and then just my regular partitioning will work?
So LLAP is basically running. So the parts like compiler and optimizer and even the execution engine, most of it is pretty much it's Hive. So whatever Hive supports, LLAP should support. So any queries with any number of joins, or like if Hive supports it, then LLAP will also support it.
Because usually in regular MapReduce way of doing the things, right, without LLAP, so it goes into the full table scan if I'm not going to have my partitioning in the where clause, right? That is how the query works. But that's why the performance degrades.
Yeah.
How does the LLAP work?
So with regard to partitioning, I don't think LLAP. So LLAP basically, so if you think LLAP is an execution substrate, sort of. So if you're talking about the higher level of compilation of the query and optimization of the query before it starts even scanning the data, you really still, so the full scan of the table, if you trigger that on LLAP, it's going to be much faster than full scan of the table on MR. But you still don't want to do the full scan of the data if you can avoid it. So partitioning is still relevant. You still want to have partitioning. If you may not need, so you may avoid the scenarios where you have to do some convoluted schemes in order to avoid, the slowness of MR on Hive 1. But if there's natural partitioning of the data that you can utilize to avoid some scans before the query even goes to execution, that is still a good thing to do. Yeah. I think that was, yeah. Oh yeah, so this is actually, I guess I should have made this more clear. This is actually a Hive feature that originally is supported and developed for Hive. But because of the access to LLAP, Spark can also utilize this feature. And I think there's actually a talk about this in Ranger during the summit, or maybe it was, yeah.
Have you done any benchmarking against Hawk? Where does this mean Hawk?
We probably have, but I'm not aware of any numbers. I don't know, somebody, Günther, are you aware of any benchmarks against Hawk? We did a benchmark against Presto, and I didn't even publish it because at least at the point where we did it, Presto was just incredibly slower, mostly because, not because necessarily of the execution engine, but because of the limitation of the SQL and high-level optimizations for the queries. I'm not sure if we ever did any benchmarks against Hawk. So HTTP 2.5 has LLAP. Unfortunately, it was a tech preview version, and we do know of some kind of pretty serious performance issues there. So it works for many people, but sometimes you can run into this terrible, terrible slowness all of a sudden. Yeah, so 2.6.1 is kind of actually not very far from, it's not like a super radical change from 2.5 in general, so, but it does have all those fixed, so it's, that's what the version we recommend.
We're in kind of a bind because Hawk is not certified with 2.6 yet.
Okay.
And LLAP, so.
Yeah, well, I don't know. You should try LLAP. I can say that much. But you can try it on 2.6. I think. I'm not sure if we're going to have a 2.5 any more updates to 2.5 other than like bug fixes and stuff like that. Yeah. that is true. I mean, it's not. I mean, I don't want to like kind of like say those file systems in the cloud are terrible. They're not terrible. They're just objectively slower than having like your disk right here. Because when you're reading from HDFS, in the best case, you actually have a channel from your process to the data node, which reads the data directly from data nodes from memory, not even from the TCP connection, right? So you obviously cannot match that if you're reading from a data without any locality from some different rack in like a different data center. So, but yes, for Mars there is not really a solution that we have, or I guess anybody has from the cloud file systems that I'm aware of.
Caching that is supported by LLAP accessible by any other means, or only through high-end Spark?
So it is. So by nature of the okay, there are kind of it's a two-level question, two-level answer, I guess. First of all, any container-based execution model is not going to support this caching because container is owned by a single user, and it goes away usually immediately after the job, or in the best case, it goes away after you close like your CLI session. So obviously, caching becomes pretty pointless. Or on a higher level, you could, as I said, we have external access, which is not user-friendly right now, but it is there, and there is code that works on top of it, and it's going to become better over time. There is external access, but it is high-level external access that is, for example, Spark SQL uses, where you can push the data scans and some logic into LLAP. So that can be accessed by anyone, but I don't think it will ever be backported into MR, because that's like too low level, I guess, to do that. Like, if you're running an MR thing that's reading from LLAP, you might as well be just running into the same thing inside LLAP. Yeah, in the back. No. So LLAP cache is, so LLAP supports org. LLAP itself can run anything that Hive can run pretty much. Org, Parquet, whatever. LLAP cache is primarily supported for org and for text data. LLAP cache support, native support for Parquet is work in progress. And as for the limitations of the cache for on-prem data, it's kind of natural that basically the usefulness of the cache is a function of the size of your data, the size of the cache, and how slow the reads are in the first place. So in the worst case, if you have a huge data set, small cache, and the fast HDFS on-prem, you may not see like any benefit from cache whatsoever. In the worst case, if you have large cache, cloud file system, text data, your query may become 40 times faster, as the case was in some cases. Obviously, it's a spectrum of things in between. So if you have a small query, so it fits in the cache, maybe on your on-prem cluster, you'll still see some benefit from cache. Again, like if you have a large query on the cloud and it doesn't fully fit on the cache, maybe you'll see some benefit, but not as much if it did fully fit in the cache. And so it really depends on the workload, yes. You can enable, so the cache is enabled by default if you're running with it. You can disable the cache per query if desired. You can also, there is no functionality. So in general, it is a feature that people ask for a lot, but we don't really like it. Because if you do, like, you're implying that you pin a table to the cache, right?
I guess at what point does a particular table get cached?
When you read it first. It's going to be slower. It's not going to be slow. It's still going to be fast. But it is going to be slower. So it is a feature that we get asked for a lot, and we might actually implement it. It is, though, it's something that should be used with caution, because in general, you don't necessarily, especially with like a typical data warehouse where the data is coming in all the time, you don't want to have someone sitting there and caching the data, because like users always want to cache more than you can actually cache. And some of the data may not actually be necessary to be cached. But it is something that we have like in a pipeline to be able to pin the data to cache and say, I want this table cached because it's very important. Right now, there is no such functionality. Is that a, yeah. So I think I mentioned, yeah, I mentioned it on one of the slides. The consistent, so we use consistent hashing with some limited amount of coordination in order to always. So basically, we have cache locality. We do not have a by choice at this point. We don't have a central cache manager. We use consistent hashing, and we coordinate some information through Zookeeper for the cases of failures and cluster size changes in order to preserve as much as possible of the cache hit rate in order to sort of get this cache locality. And you can configure, so the way you configure is there's a setting, it's on the slides, which I skipped, that will be on SlideShare. There's a setting for cache locality delay, so to speak, which basically means how long should we wait to get the local container, to local fragment execution. If you set it to strict, which means always run where the cache is, you'll pretty much guarantee the cache hit. And as you relax it and set the timeout lower and lower, you can set it to 0, in which case it won't wait for the locality at all, and it will basically run wherever, in which case, yes, the cache can get replicated. But what we found out is that in some cases, again, really depends on your workload. In some cases, that is actually a desirable property. As I said, if you have 1 hour of data that everybody is reading, you actually do want to replicate this 1 hour on every node, which will happen kind of automatically if you relax cache locality to say, I don't necessarily want to have locality. I just want it to run somewhere.
One quick follow-up. So, is the LLAP support relevant when Hive is running over HBase, for example, or in that case it doesn't?
No, that is not generally supported. So okay, let me backtrack. You can run queries that you read from HBase because it's the same thing that Hive can do. That means LLAP can also do it. You can run HBase queries on LLAP, and all the execution level improvements, like for example, all the preemption and stuff like that, that will still kick in and it will be supported. The entire cache layer will not be used for queries using HBase accumulate, etc. Well, HBase has its own cache layer, so it's kind of moot. Yeah, I guess we're done. Thank you.